Today we're diving into a super cool problem, finding the value of this integral t, which is the integral from negative infinity to positive infinity of e to the power negative x squared dx. This is called the Gaussian integral, and it pops up all over the place in math, physics, and even probability. It looks tricky because there's no easy way to find an antiderivative for e to the negative x squared. But don't worry, we're going to solve it using two methods. Let's get started. Let's kick off our first method to solve this integral, the 3D polar coordinates approach. We're trying to find the value of t, which is the integral from negative infinity to positive infinity of e to the power negative x squared dx. This is called the Gaussian integral, and it's super important in math, physics, and probability. It's a tricky one, but we're going to nail it with a clever trick. Let's dive into the math. All right, here's our first big idea. Instead of tackling t directly, let's think bigger, literally. We're going to compute t cubed, which is t times t times t. That means we take our integral, which is e to the negative x squared dx, and multiply it by 2 more just like it, but with y and z instead of x. So we have the integral of e to the negative y squared dy, and the integral of e to the negative z squared dz. Multiply 3 integrals, x, y, and z. When we multiply these together, we can combine them into one giant triple integral over all of 3D space. That's the integral from negative infinity to infinity in x, y, and z of e to the negative x squared plus y squared plus z squared dx, dy, dz. This looks intense, but it's setting us up for something awesome. Now, this triple integral is a beast, but we can make it way easier by switching to spherical coordinates. All right, let's transform our triple integral using spherical coordinates, but this time we're going step by step to make it crystal clear. First, we plug in our coordinates. X squared plus y squared plus z squared becomes just r squared, so our integrand e to the negative x squared plus y squared plus z squared simplifies to e to the negative r squared. Awesome. Now we need the volume element dx, dy, dz in spherical coordinates. Remember, x equals r sine theta cosine phi, y equals r sine theta sine phi, and z equals r cosine theta. To change variables, we use the Jacobian, which gives us dx, dy, dz equals r squared sine theta dr d theta d phi. Our limits are r from 0 to infinity, theta from 0 to pi, and phi from 0 to 2 pi. With all that, we can rewrite our triple integral as t cubed equals the integral from 0 to 2 pi in phi, 0 to pi in theta, and 0 to infinity in r of e to the negative r squared times sine theta dr d theta d phi. This is looking so much better. Okay, we've got our triple integral looking nice in spherical coordinates. Now let's make it even simpler by splitting it apart. Notice that our integrand e to the negative r squared times sine theta doesn't mix the variables phi, theta, and r. They're independent. That means we can separate this triple integral into 3 separate integrals. One for phi from 0 to 2 pi, one for theta from 0 to pi with sine theta d theta, and one for r from 0 to infinity with e to the negative r squared times r squared dr. This is huge. It breaks our big problem into smaller, bite-sized pieces. Now it's time to crunch some numbers. We've split our triple integral into 3 parts, so let's evaluate each one. First, the phi integral from 0 to 2 pi of d phi is just phi, evaluated from 0 to 2 pi, which gives us 2 pi. Easy. Next, the theta integral from 0 to pi of sine theta d theta. The antiderivative is negative cosine theta, so from 0 to pi we get negative cosine pi minus negative cosine 0, which is 1 plus 1, or 2. Now the r integral from 0 to infinity of e to the negative r squared times r squared dr is trickier. Let's use a substitution. Let u equal r squared, so r is the square root of u, and dr is 1/2 u to the negative 1/2 du. This turns our integral into 1/2 times the integral from 0 to infinity of e to the negative u times u to the 1/2 du, which is 1/2 times the gamma fun of 3 halves, or 1/2 times the square root of pi over 2, giving us square root of pi over 4. Multiply all 3 together. 2 pi times 2 times square root of pi over 4 simplifies to pi times the square root of pi. We're so close to finding t. Here we are at the finish line. We've found that t cubed equals pi times the square root of pi. To get t, we just take the cube root of both sides. So t equals the cube root of pi times pi to the 1/2, which simplifies to pi to the 1/3 times pi to the 1/6, or simply pi to the 1/2, which is the square root of pi. That means our original integral, the integral from negative infinity to infinity of e to the negative x squared dx, equals the square root of pi. We did it. This is the famous Gaussian integral solved using a super clever 3D trick. All right, let's switch gears and solve this integral using complex analysis. It's like math magic. We're going to work with a function in the complex plane, f of z equals e to the negative z squared. This function is super nice because it's entire, meaning it has no singularities or trouble spots anywhere in the complex plane. That's perfect for what we're about to do. Let's dive in. To solve this, we're going to use a special path in the complex plane called a contour. Picture a wedge-shaped loop with 4 parts. First, we go along the real axis from negative r to r. Second, we go straight up from r to r plus I times r. Third, we travel along a diagonal line at a pi over 4 angle from r times e to the I pi over 4 to negative r times e to the I pi over 4. Finally, we come back down from negative r plus ir to negative r. This loop is our key to unlocking the integral. Let's see how. Here's where the magic happens. Because our function e to the negative z squared is entire, Cauchy's theorem tells us that the integral around our closed contour equals 0. That means the sum of the integrals over all 4 parts of our wedge-shaped path adds up to nothing. This is going to help us find our integral t. Let's evaluate each part of the contour. First, let's look at the part along the real axis, where z equals x, going from negative r to r. The integral here is just e to the negative x squared dx, which as r goes to infinity is exactly our target integral t, the integral from negative infinity to infinity of e to the negative x squared dx. This is the piece we want, so let's keep it and check the other parts. Now, let's check the vertical line from r to r plus I times r. We set z equal to r plus iy with y going from 0 to r. The integral becomes I times the integral from 0 to r of e to the negative quantity r plus iy squared dy. Expanding the exponent, we get negative r squared minus 2iry minus y squared. The magnitude of this is e to the negative r squared plus y squared. Since r is huge, e to the negative r squared is super tiny, making this whole integral vanish as r goes to infinity. So this part contributes nothing. Next, we tackle the diagonal line, which is at a pi over 4 angle. We set z equal to t times e to the I pi over 4 with t going from r to negative r. So dz is e to the I pi over 4 dt. The exponent becomes negative t squared times e to the I pi over 2, which is negative I t squared. The integral is e to the negative I squared times e to the I pi over 4 dt from r to negative r. To make it cleaner, we reverse the limits, which adds a negative sign, giving us negative e to the I pi over 4 tar times the integral from negative r to r of e to the negative it squared dt. This integral is interesting. Let's hold on to it. For the last part, we go down the vertical line from negative r plus ir to negative r. Set z equal to negative r plus iy with y going from r to 0. The integral becomes negative I times the integral from 0 to r of e to the negative quantity, negative r plus iy squared dy. The exponent is negative r squared plus 2iry minus y squared. The magnitude is e to the negative r squared plus y squared. And just like before, e to the negative r squared makes this super small as r gets big. So this integral also goes to 0. We're almost there. Now let's use Cauchy's theorem. The sum of the integrals around our contour is 0. We've got our real axis integral, which is t as r goes to infinity minus e to the I pi over 4 times the integral from negative r to r of e to the negative I t squared dt plus the 2 vertical integrals, which we found are 0. So we're left with t equals e to the I pi over 4 times the integral from negative infinity to infinity of e to the negative I t squared dt. That integral looks fancy. Let's figure out what it is. That integral, e to the negative it squared from negative infinity to infinity, is called a Fresnel integral, and luckily we know its value. It equals root pi times e to the negative I pi over 4. This is a standard result in complex analysis, and it's going to help us wrap this up. Let's plug in our Fresnel integral. We have t equals e to the I pi over 4 times root pi times e to the negative I pi over 4. Notice that e to the I pi over 4 times e to the negative I pi over 4 is e to the power I pi over 4 minus I pi over 4, which is e to the 0 or 1. So we're left with t equals root pi times 1, which is just root pi. We did it, and there's our answer. The integral from negative infinity to infinity of e to the negative x squared dx is root pi. This complex analysis method with the pi over 4 contour was like a math roller coaster, but we got the same result as our 3D method, which confirms we're on the right track. Thanks for joining me on this journey, everyone. Hope you enjoyed it as much as I did.